Hello, my name is Eric Dolores Cuenca, and the purpose of my talk is to explain how we use Mathematica to discover new identities in combinatorics. This story starts when I was working with artificial intelligence. We had meetings with groups from neuroscience because we wanted to know if there are some strategies or properties of biological neurons that we can use in artificial neurons. And in one of these meetings, the people from neuroscience told us about the following problem. Assume that you have different neurons connected in this particular way. One neuron in front of the other, and the neurons, when they are excited, they fire a signal to the neuron in front and to itself. Now, to excite a neuron, you can use an external stimuli, like sound, or you can use an internal stimuli, meaning that the neurons receive two signals at the same time, and those signals were fired by other neurons. So in this movie, you can see how by applying different external stimuli at different times, we obtain, we can see the flow of signals through the system. And here the idea is that the last neuron is activated only because the previous neurons were activated at a particular time. So these systems are called polychronic groups. Poly is for several and chronos is for time. And the question that we were asked is, given the number of neurons in a line, and given the number of external stimuli applied, if we can count all possible configurations of polychronic groups. The first thing that we review is if this problem can be related to problems in other areas. One of the things that people in this conference might have realized by now is that this is a cellular automata 192. For this automata, we use the following rule. Here, the vertical line is time, and the middle square is going to be black only if at the previous time, that same square was black and the one to the left was black. So under this rule, we see that in our case, a neuron is going to be green only if previously that neuron was activated and the one on the left was activated. In other words, every time you see two neurons, the one on the right will be green and the next iteration. And you can see here that that's the case. And so this is cellular automata 192, where you are allowed to correct the output of the automata at different times. Another place where this kind of diagrams might be useful is in the study of social media. Have you ever thought about why do you retweet a post? Using psychology, we can imagine that there are two cases. Whenever there is an external stimuli, like somebody pays you to retweet, and it doesn't matter what is the content of the message or who sent it, you are paid to do it, you just do it. And whenever there is an internal stimuli, whenever you agree with the content, or because all your friends are sharing that post, or in case that you want to manage your image, you are looking for a job, so you want that the people is looking for employees. Whenever they look at your profile, they find particular information, or also in case that you want to send an indirect message. So maybe you got angry with somebody and you're going to put a post on your profile. And even if you don't tag the person, whenever that person visits your profile, they will see that message. Here, the important part is that this is a non-linear system. By that, I mean that you are going to retweet if any of these operation and if any of these conditions holds, but if more than one holds, you only retweet one time. So if the sum of the number of conditions that are true is bigger or equal to one, then you retweet. Now, once we found that this question is not an isolated question, but that actually can have interpretation in other fields, let's go back to the original problem. So we have neurons, and the neurons are in this very particular configuration in which one neuron is in front of another. And when a neuron fires, it sends a signal to itself and to the neuron in front of it. And you can make a neuron fire either by sending an external stimuli, or if the neuron receives two signals at the same time. It is easier to see this through time. So the vertical axis now is time. On the left, we see the external stimuli, and on the right, we see the neurons that are activated. And this should convince you that this is a whole system working together, and that, in fact, the last neuron is activated only because all the others were activated at a particular time. Another thing that you might see from these diagrams is that triangles are important. In fact, the previous system can be described as the operation of stacking a triangle into the other from below. Here, the only requirement is that we do not allow the top vertices to coincide. And the first thing that we prove is that if now we only care that the neuron is activated, so here color black means that it is activated either by internal stimuli or by external stimuli. And so if we look at these diagrams over time, then the configurations of polychronic groups in this family of neurons is a disjoint union of the diagrams that you are seeing in the screen. In this diagram, it looks like you have a line, but when you zoom in, you realize that these are just triangles stacked into each other. And we prove that this family of figures always have a top triangle that we consider the soil. And here below you have an object called a chinampa, agricultural technique in Mexico that also has the soil. And in a chinampa, you might have a tree going out. And in our case, our graphs also have a tree going out. And the chinampa has roots, but we don't have any control of the roots in our graph. They can be bigger than the soil, and the roots can have roots. All we know is that the roots are pushed to the left as if there is water pushing them, just like in a chinampa, where the direction of the water is going to push the roots in one same direction. So we call these objects chinampas, and once we found a topological classification of these diagrams, we wanted to see if we can count them. But here we found a problem because the roots, whenever two roots touch each other, the white part in between becomes black. And so we needed to understand when are two roots going to collide, and the collision can happen almost immediately, like here, or maybe the roots are going to grow for a while and eventually they're going to move to the left and they're going to collide. So we need some sort of combination of combinatorics and topology, which is commonly known as algebraic topology. So we studied a simplified case in which the chinampa looks like this, and we fix the number of roots and we fix the height of the roots, and the roots can only be done by using triangles of 2 by 2. So here n is equal to the number of roots plus 1. And now to prevent them from collision, there should be at least one wide space between two roots. N, again, is the number of roots plus 1. So when k is equal to 1, when the height is equal to 1, we found that there are as many configurations as n. And for that, we usually study a generating function. So you have the sum of x to the n multiplied by the number of solutions to the system, in this case n. So you have the sum of n x to the n. Now, when k is equal to 3, we are going to assume that we have some bubbles of air, and the position of the bubbles of air, they are going to push the roots. And so there is an equivalence between the position of the roots and the position of the bubbles of air. What we found is that the position of the bubbles of air can be described by a solution to the system. So the system says that I have these inequalities, 5 variables, and there is an extra variable that satisfies this inequality, where the smallest should be bigger or equal to 1, and the largest should be smaller or equal to 7. For example, the first configuration, in which the roots are vertical, corresponds to this solution, and the last configuration, in which the roots are in diagonal, corresponds to this solution. So when k is equal to 1, and given the parameter n, we find n solutions. So here I draw a partially ordered set. There is just 1 point. And for every label that you put on this set using numbers from 1 to n, you find a configuration of the roots. And this is the corresponding generating function. When k is equal to 2, we found this partially ordered set. Here the order says that if a point is left to another point, then the point on the left is smaller than the point on the right. And so for every way in which you can put labels preserving the order on this poset, then you have a configuration of solutions, and this is the generating function that corresponds to this system. I showed you that for k equal to 3, the poset looks like this. And so for every way in which you put labels, you find a solution. Every way to put labels on this poset is equivalent to choose where to put the bubbles of air. And so we use Mathematica to find this generating function. And as k grows, the poset becomes more complicated, but at the same time, we were able to compute the corresponding generating function. And we discovered something surprising, that the coefficients of the power series have some symmetry, which for once shouldn't be that surprising, because so topological objects have a symmetry, but at the same time we don't understand the meaning of these numbers and why there is this beautiful symmetry of going left to right or going right to left. So this is the evidence that motivates you to find a theory that goes from graphs to power series. And this evidence, my next goal is to explain you how we obtain this evidence using Mathematica. So the idea is the following. I start with a line that has S points, and we build one of these graphs over it. And so we have this geometric transformation of a line into a graph. And then we wonder if we can transform the generating function of the line with S points into the generating function of the graph. Now, if you have a line with S points, and I ask you how many ways can you put labels using n numbers, you just need to choose S out of n. So this is the generating function of the line. And the idea is to find an operator so that after applying the operator, we obtain the generating function of y. And so the strategy is we use symbolic computing to determine the generating function of y. That is given by some coefficients that are actually polynomials in n. Remember, these coefficients tell me all possible ways to put labels on y with numbers from 1 to n. We actually ignore the coefficient, the binomial coefficient here. This is something that it can be explained in the paper. And the way to create the differential operator out of the coefficients is that we replace every instance of n x to the n by this operator. You agree with me that this is the same value. And then we replace any instance of n squared x to the n by this operator, and so on. So this is how we read the differential operator out of the values computed with Mathematica. So here is an explicit computation. I'm going to have a line with 13 points, but in fact, the first and the last don't participate. So everything here is going to be computed using 11 points. Now, given 11 points, how do I find all possible ways to put labels using numbers from 1 to n? Well, the first point can have the value 1 all the way to n minus 10. The second point can have the value a plus 1 all the way to n minus 9, and so on. And so we compute this value and we keep it in memory. Now, we are interested in a little bit, something a little bit more complex than a line. What we have here is this graph. And we also ask Mathematica, how many ways can you label this graph using numbers from 1 to n? And this is the corresponding expression. And once you have this expression, you need to divide, you need to remove the binomial coefficient. And what we obtain is this polynomial. Now we transform this polynomial into a differential operator. So we multiply the first coefficient by f, and here we change this n by x derivative, and then we have this n squared that is changed to x derivative, and we need to do this to the whole operator, and this is something that I believe took a week in a Mac, and you can see that, this is something that definitely needs computer help. But at the end, we simplify, and when we expand, you see that there are these coefficients, 1, 99, 3, 1 to 9, and if you read them backwards, you get 1, 99, 3 to 9. So this is how we use Mathematica to predict this power series, and once we are in this position, then actually this is how we compute the last one. Once we have this evidence, then it's time to do math. So we have this evidence that symmetries of graphs are translated into symmetries of the power series, and we were able to develop, actually to rediscover a theory of order polynomials, but we use a different point of view, and thanks to that point of view, one of the results that we have is the following new combinatorial identity that says that if you have n and you have a k partition of n, then for a m big enough, the binomial coefficient can be written in this formula. Here you are assuming over partitions of m, k partitions. And another result from our point of view is that you can compute the binomial coefficient as a sum over partition of products of numbers. So you can compute the binomial coefficient without making any division. Now, in this conference, because people here knows how to program, they recognize that it's a much harder problem to compute partitions than to compute a division. So this is perhaps not that interesting for people that actually program. Another identity that we found is that you define this symbol as the number of ways to write A as a sum of B numbers so that each one is greater or equal to 0. For example, n of 3,2 is all the ways, the number of ways that you can write 3 as the sum of two numbers where they are greater or equal to 0. Then the function n satisfies the following identity. So these are results of the theory that we built after obtaining the evidence from Mathematica. However, our theory only reaches the first three graphs. We still don't have a theory that explains how do we get from k greater equal to 4 to the power series on the right. So this is still an open problem. And I guess I won't see the last line. I wanted to conclude my presentation by saying that there is another open problem that appears in our investigation. We believe that 49 times 2 to the n always has an odd digit. We have made experiments and we have showed this is true for n small equal to this number. So in particular, in this case, here is the odd digit. This is a problem related to the theory of Chinampas, but it's still an open problem. And the information that I gave to you comes from these two papers with my corresponding colleagues. Thank you.